So again, we're setting up conservation of energy for flow moving down a conduit that we can see through, this magic conduit that we can remove the conduit and the flow still moves through. Okay, so we're looking at the cross-section of an open channel here. I've got the energy coming in. There's no pump or anything else adding additional energy, so it's just the Bernoulli terms here going in. Going out, we've got the same Bernoulli terms going out. Right, the baric energy, the kinetic energy, the baric energy, the kinetic energy, and the potential energy going out. And then there's, because we've already talked about Chapter 8, we said, look, we know fluid flowing over a surface is going to lose energy. So let's see if we can quantify that energy loss, that head loss there. Okay, so working in the head form, we'll call this the head loss. Now here's the thing. Within this fluid, there's a Y value here, the depth, if you will. Right? Y is the depth in the fluid. The Z value is the elevation. This is Z1, this is Z2. We're saying, look, maybe the fluid is deeper here than it is there. And if you've got a stream or a river flowing through, sometimes at one point in the stream it's really narrow, and at a later point in the stream it's actually very deep. And that's what we're trying to describe there. So what we have here is if I've got a depth here and a depth there, and if I say, well, let's take points on the very bottom of the fluid channel, then what I've got then is P1 is equal to this density of the fluid times gravity times not Z1, Y1, right? Rho G Y1. That's going to determine the pressure right there at point 1 based on how much fluid is above it. And the same thing at point 2. P2 is going to equal rho G Y2. Okay? Now notice I've got, so I'm saying put this right here, well that's rho G over rho G, so that's going to be then Y1 plus V1 squared over 2G plus Z1 is equal to Y2, the depth at 2, plus V2 squared over 2G plus Z2 plus the head loss. Okay, so all right, what does that, Steve, how does that help us? Well, let's see what we can do with that. Now recall back over here a few steps ago I said, well, we can define this bottom slope as the length from here to here times this S naught. That gives me the change in elevation. Well, I've got a change in elevation here, Z1 minus Z2, or vice versa. Right? So if I do that, I can say this. I can say, well, sorry, I'm looking at my notes here. I'm saying that if I take this expression, I can, let's do this. Let's say Y1 minus Y2 right, plus Z1 minus Z2 is equal to, let's say, V2 squared over 2G minus V1 squared over 2G plus the head loss. Kind of group those together there. Okay? And again, I'm saying, well, let's change this into the bottom slope. S naught times the length. Again, S naught represents the change in elevation per unit length times the length. That gives us the change in elevation. V2 squared minus V1 squared over 2G plus the head loss. Okay? So that would be conservation of energy for an open channel flow. So as the depth changes, the kinetic energy changes, as the bottom slope changes, and as the head loss. These are the four factors: the depth, the elevation change, the change in kinetic energy, and the head loss. All interrelate to one another. Okay? Alright. So here's the thing. We could use Chapter 8 principles and say, well, the head loss is equal to, of course, FL over D, V squared over 2G, and then maybe plus a minor loss if you've got a minor loss there. But if it's mostly straight stream, there's no bends or elbows, it's just go find a Darcy friction factor. This is okay. Nothing wrong with this. But there is actually another concept that works really good for open channel flow. It's called the Manning equation. Right? So the Manning equation what this does is it allows us an alternative, let's say, to finding the Darcy friction. Let's say it that way. Alright, so with the Manning equation, we don't have to find this Darcy friction factor to find the head loss. It's still based on this principle up here. Now, the Manning equation does assume uniform flow, so we can only really apply it in situations where the depth is constant. Uniform flow says the depth is constant and the average speed. And you don't even have to square that. We're just saying the average speed is constant. So if the depth is constant through multiple points in the flow and the average speed is pretty reasonably constant throughout the flow, this change goes to 0, this change goes to 0. I'm left with this, right? The change in elevation basically is in equilibrium with the head loss. So if the change in elevation is in equilibrium with the head loss, these guys actually end up equaling each other out. And that's what causes uniform flows. If these two are in equilibrium with each other, then these two have to be in equilibrium with each other. And the easiest way for that to occur is for them to be constant. So if they tell us we're dealing with an open channel with uniform flow, that means these guys are 0. That means this equals that. Right? And so rather than having to find a Darcy friction factor, we have a couple of expressions here. The Manning equation says, well, that the speed, all right, and they like to use V naught, that's the speed, the average speed within the flow, is equal to a correction factor, just a dimension correction factor, right, divided by the Manning coefficient, the N value. So A over N times the hydraulic radius raised to the 2/3 power times the bottom slope raised to the 1/2 power, or square rooted. So the square root of the bottom slope, the hydraulic radius squared, and then the third root, or 2/3 power, and then A over N. And then the volumetric flow rate, which is just going to be the speed times the cross-sectional area. So the volumetric flow rate is going to be A over N times the cross-sectional area times these other things, the hydraulic radius to the 2/3 power and the bottom slope to the square root of the 1/2 power. Okay? And so that's where A is this correction factor. A is either equal to 1 meter to the 1/3 power per second, which is weird, I know, but you need that for the units to work out, because this is going to be in meters to the 2/3. So to make this work out, you need meters to the 1/3. Okay. Anyway, and in the English set, that ends up being 1.486 feet to the 1/3 power per second. How do we get that? Well, we'll take whatever 1 meter is in feet as like 3.2 something. Take the third root of whatever meter to feet is, take the third root of the number, and that'll give you this, I'm betting. You can double check that. N is the, what we call the Manning coefficient. And this is just a plug and chug formula. If I know it's uniform flow, I can use one of these expressions. I need to know the bottom slope and the geometry of the conduit to find the cross-sectional area and or the hydraulic radius. And then I need to know what is the composition of the stream. What is the roughness, essentially? This has to do with the roughness of the material. You're going to hear a pop here. Okay, how am I on time? Okay, we got time here. So this is in your in your text. This is table 13.1. You can see these are Manning coefficients. These are N values for various surfaces. You can find this in your text. You can see I put some tabs here, so put you some tabs in your text on this guy when you take your final so you can get right to this. There will be a Manning equation on the final. You can see as you get into rougher surfaces, so for glass, which is typically smooth, it's a very low Manning coefficient. When you get up here to rougher surfaces like mountain streams or farmland or masonry rubble, that's a much higher Manning coefficient than smooth surfaces are. So anyway, it essentially serves as the roughness for your conduit. Okay, so the smoother it is, the lower the Manning coefficient. The rougher it is, the higher the Manning coefficient. And that inverses, or that affects, then that either slows down or speeds up the flow accordingly. Okay? All right, I think that is, so that is, there's your homework assignment, which I've already posted on Canvas. It is really a pretty straightforward plug and chug. You just have to know the geometry of the conduit to figure out the hydraulic radius and the cross-sectional area. Go look up a Manning coefficient. Do some units. These normally are pretty straightforward. These normally are not too terribly difficult, but there's some homework there to get you a little practice before the final comes out. So again, that final's in a couple of weeks, but we do have exam 3 coming up next week for chapters 8 and 11. We'll talk about that next time. All right, guys, stay safe out there.